Okay, so let's continue, everyone. I hope everyone has completed up till mini challenge 2. I hope you got some time to kind of see some articles, how they are being used, some of the fake articles, some of the real articles. Does anyone have any comments about the articles they saw or any thoughts? Um, Even if you have any thoughts about the approach we are taking, or even general thoughts like how would you want to do it, how would you go ahead and use machine learning to solve this problem? Okay, so let's do a more careful visualization and detailed analysis of this data set. So let's see. If you remember, I said that there is a subject mentioned in this data set. Let's see how many news articles belong to different subjects. So here I'm using this plot library. It is plotting this figure and it's doing nothing but plotting the count of each article, the count of articles in each category. So let's say in political category, there are more than 10,000 articles. For Middle East category, there are least number of articles. For specifically US news, there are no articles. But essentially, all the other articles are indeed related to US as of now. So there are some world news articles as well, which are near to 10,000. And then there's the general news, there's politics, etc. Okay, let's have another challenge here. Can you plot the count plot for fake versus true news? So right now here we have plotted the subject column. Can you plot how many articles how many articles we have in the fake category and how many articles we have in the real category? I would give you a hint. You use exactly this code and all you have to do is change the name of the column. So give it a try. Anyone who has a plot? You may not be able to share it, but just raising hand that you are able to make it would be a good thing. Okay, so Mayanka was able to plot it. So like I said, so we can use this particular piece of code only. And interested is knowing about this is fake column. So if you see here, you can see we have this is fake column, which can basically tell us the amount of fake articles versus real articles. So if you run this, you will see how many articles have the label 1, how many articles have label 0? And they are more than 20,000 for each one of them. The data set looks pretty balanced, as in the articles for the fake category and for the real category are quite close to each other. Okay, now let's do something more interesting. Let's see which words are very common in this text. For fake articles, let's see, or for the genuine articles, let's see which words are very popular in genuine articles versus which words are very popular articles. Because one way of kind of approaching this problem could be, let's say if Trump is mentioned in a particular article, it is more likely that it is fake because there is a lot of misinformation being spread about Trump. Or maybe you can say if there is a news article which has some weird mentions, then you can say that these articles are fake versus real. So let's see, is there a relation between which words are present in the fake articles versus true articles? And can we see if we are able to predict based on those correlations? So again, we library. This word cloud is a library which will give words are most common. So essentially here I'm using this data frame where is fake equal to 1. So this was for real articles. Among real articles, I'm trying to see which particular so we can run this cell. There are a lot of articles. This cell will take a kind of tell us. But what these arguments essentially are saying is I'm looking for only top 2000 words. Top in the sense by frequency. So let's say this particular function will rank all of the words by their frequency of appearance. So if a word appears 10,000 times and it is maximum, then it is ranked in the list. But if a word only appears once, then it would be somewhere down in the list. So we're looking for only top 2000 words. And width and the height is the dimensions of the plot we will see. And here again, we exclude the stop words because if you count it, stop words such as the, is, am, I, we, they are words which have very, very high frequencies and they are not a useful indicator of fake or real articles. So we are ignoring those stop words. Okay, so our plot is ready now. And if you see in the real articles, such as Donald Trump, United States, White House, North Korea government are quite low. So Washington and Reuters, etc. So these are the top words that are visible in real articles or are often mentioned in real articles. These plots are called word cloud plots, and here the more bigger a word appears or the more bigger or bold a word is, that means it has the most highest frequency. So this means that Donald Trump in United States are probably the top 2 words in this particular set, real article. And as the frequency goes down, the word get tiny and tiny. This particular approach can be useful for any data analysis. It's not necessary for fake or news articles, and it is widely used for exploratory analysis where you just want to do a check what exactly is in your data. So you just want to see how does it look like, which are more common, which words are less common, like that. Now let's do this for fake articles also. We'll plot the word count for text that, so again, I'm using 2000 words. So let me run this because it's going to take some time. So here I've used df.is fake equal 0, meaning all of those articles which are fake. Plot the word cloud for those particular words. And let's see how the word cloud like and how does it compare with the word cloud for the real articles. Mm. So any questions while our code is taking a little bit of time to kind of run? Okay, so here we go. So we now have this word cloud. And if you see here, again, Donald Trump is common in fake articles as well. But now you see some other words too, like Hillary Clinton, president, time, Twitter, America. But United States was also present earlier, featured, image, etc. Said, and time. So there is an overlap between words in fake news article versus real news articles. There is some distinction. And this is exactly what we're going to use to train a model. So there are some words that can be leveraged to to train a neural network model to be able to predict whether a particular news article is fake or is it real. So I think one of the participants had asked, how are we going to do it? This is the bigger picture now. Like some words appear more frequently in fake news articles. Some words appear more frequently in real world articles, real news articles. And can we use that distinction? Can we use that distinction in field kind of train a neural network model and then predict this classification label for any new article? Okay, now let's also quickly note down what is the length of the maximum document for each particular document we have. So here, so for instance, let's see. Let's see, this is the first particular article. And if we see what is the length or the number of tokens for this particular article, it's 3088. So we want to know how many maximum number of tokens are there. Sorry, this is number of characters. You can tokenize it, know how many appear in a particular document. So this particular document has only 383 tokens, but I want to know what is the longest document and how many tokens are there, how many words are there in that particular document. So let's, this code is very simple. So for each document, we find its tokens. We use this word tokenize library to find the tokens. It's just splitting on spaces while taking care of full punctuation marks. And if the max length is length of tokens, you are finding the maximum value for each of these length of tokens. So let's run this. And this is a loop over so many documents. It's going to take a little while. The reason why we are doing this is we are now going to transform these words into numerical vectors. And like I said earlier, we need to know what is the vocabulary, and we need to know how many dimensional in vector do I need to create for each document. So we'll create a vector for each document where each dimension would correspond to a word. So let's this run quickly. Okay, so are you guys able to see if I'm drawing something here on the side of the notebook?
Yes, it's visible.
Okay. So let me give you this idea of how I'm going to use the word tokenization here. So let's say my vocabulary has basically words only. Let's assume the size of the vocabulary is only 5 actually. So it has W1, W2, W3, W4, and W5. So those are the only words that I have in my world. So let's say this is an alien world where you can only use 5 words. That's your total vocabulary. And you can use as many sentences as you want using these 5 words, but no other word is allowed. So now if the alien from W4, W3, representation to denote this word into a vector format. So you need to a vector representation here. Let's say this is what Bob said. Let's say Alice said something else. She said W4, W1, she said W2, and then she said W5. And now you need to represent this into a vector. Note that Bob only said 3 words. Alice said 4. And we need a way not only to represent each one of these as a number, but also a way to represent these as uniform vectors. So each one of these should always be there. So if you understand, so the input can be variable dimensions. It has 3 dimensions here, 4 dimensions here, but the output you want always should have d dimensions. And a way to do that is basically you take this vocabulary, you assign an index to each of these words 1, 2, 3, 4, 5. Now I will map W1 to see what is its index in the vocabulary. It's 1. So Bob said 1. Then W4, Bob said 4. W3, Bob said 3. That's done. Let's assume to 5 in our case. Now for Alice, but this vector is only 3 dimensions. So we'll come to this point later on, how we construct a 3-dimensional vector into a 5-dimensional. But let's now concentrate on Alice. So Alice said word 4, Alice said word 1, word 2, and then word 5. So now Alice has a 4-dimensional vector, Bob has a 3-dimensional vector. Then we use this concept of appending zeros at the end to make these vectors uniform. This concept is called padding. So what we essentially do is, there are 3 numbers. I want 5 dimensionality. So I will append 2 zeros in this vector. Here for Alice, there are 4 words. There's 5 dimensionality. So I'll just append 1 0 vector. And this is how we will convert our text data into its numerical format. And note there's a mapping between each word into a number. So that would be helpful in actually helping the model to kind of keep this relationship intact, while at the same time use numerical version of the data. So any doubts in this concept? This concept is called essentially word embedding creation or the tokenization process. Okay. So now let's look at the code now here. So this is the reason why you need to know the maximum number of words in a document, because you need to find what this D should be. This D equals to 5 is because I know a vocabulary has 5 words. You can have W1, W1, W2, W2. You can construct a very long sentence with just 5 words also. You can repeat 100 times and still create a text out of it. So what we are doing here, using our training data to identify what is the maximum length of a particular document, so that I would know what is the length of this, what is the dimensionality I should use while constructing my vectors. So we find these maximum number of words in a particular document. If you run you'll essentially approximately numbers in a particular document. Next, we are going to also plot the distribution of number of words in the text to get an idea of how these words are, like how long these passages are in general. So this is, okay, now we see the maximum number of words in a particular document is like 4,406 words. Next, we draw this distribution, which is the histogram of how the lengths distributed. So on this, we have of tokens in a particular passage. On the y-axis is the number of articles with that many tokens. So essentially this here says, what says is that there are approximately 150 to 200 documents. Um, there are approximately 9,000 documents in our dataset, which have 150 to 200 tokens. Then there are approximately 7,500 documents which have approximately 200 to 250 tokens in them. So you can use Plotly library to kind of plot this thing, and then it's an interactive plotting. So essentially, I can interact with the plot. I can also zoom in into certain sections of the plot. I can double click to zoom back. I can look smaller sections where I want to zoom and check, okay, what are the, how is the count distributed here? So if we see here, there is only 700 articles, there are only 100 articles which have 700 to 750 tokens. And I guess we have only one article which would have that maximum number of tokens here. So if you can see here, this maximum number of tokens was 4,406, and there's only one article which exists here which has that many tokens. So very few articles have that huge number of tokens. A lot of articles have somewhere between 0 tokens. Okay, so now we discuss this concept of performing tokenization and pad in order to convert the data from format to numerical format. So again here, we will use this tokenizer to kind of tokenize these sentences, and then cut each of those tokens, map them to an index in our vocabulary, and therefore the input sentence then can be a sequence of numbers on your end. Now, there is an important concept of training and testing in the classification mode. Before I go details, let me quickly go over some basic concepts here. The typical pipeline of machine learning. So essentially, this is machine learning pipeline in general. What we have is we have the raw data and its labels, and then we do some sort of pre-processing and split it into training data and test data. How many of us are aware of this pipeline, or do you want me to go into more basics here? This would be a good time to kind of review the basics here. Let's basics. So in general, machine learning, we have a data set where we are given so many samples. These are xi's that we discussed earlier. And then each of these samples has a class label. So for example, this is the flower data set where you have the length of the width of its sepal, petal length, and the petal width. Essentially, a particular flower, its some features are given, and for each data, these features, and then you predict the class label for that particular feature. Now, for participants are usually manually annotated in case of supervised learning framework. There are other frameworks where you don't have access to these, but as unsupervised machine learning or reinforcement learning. For today's talk, we'll focus on the supervised learning framework. So you'll have, looks like very similar to our fake news detection problem data sets that I've shared, and these features, this here, the title here. But if you see here, these features here are numerical features. These sepal length, sepal width, or petal length or petal width, these are numerical values. However, in the text, we have long sequence of words, and we cannot just use them directly in any machine learning model. And what we are doing there is, instead of having sepal length as one of the feature vector or the feature column, we are using one word as a feature column. So the word US becomes one feature. The word Donald becomes another feature. The word Trump becomes another feature. And this is why we have a vocabulary, and we are using entire vocabulary as a feature, a number of features. So here, if you had a vocabulary of only 4 words, then this data set would make sense here, that you have only 4 words and you can construct sentences using those 4 words. But then you have just these 4 words and you use those 4 as features. For real problems, there are much more words. So for our fake news problem, for instance, we have I think double the amount of we had somewhere around 4,000 or even more words in our data set, and all those words will become a feature vector. And the class label here is the kind of flower. So it is setosa versus versicolor, but in 2 classes, so it's just real or fake. This data can be numerical or categorical. So either you can have discrete continuous values, or you can have categorical where you have nominal ordinal. Let's leave out the categorical for now. For numeric, you can have discrete or continuous. Here in this case, this sepal length continuous valued value here. So you have 3.5, 1.0, 0.2, etc. If based on what I know for words, we are mapping dictionary index, and those are always good. So we are operating numerical domain, discrete data setting. So only integers are going to be allowed. So let's skip this for now. Now, once you're done with the processing of the data, we split the data into 2 halves, into a training half, and then we split it into a testing half. So this training data set will be you to build your model. That is, you will train your model. So you will basically use gradient descent algorithm on top of this training data to update your weight parameters. But this testing data is where you will check the performance of your unseen data. This is very similar to class work we provide to our students, for example, where in the training phase, you're providing lectures, you're providing homework assignments to students, and those students are asking questions to you, and you're giving them answers. So those are like labels where a student asks you a question and teacher responds back that answer. But in the testing phase, this is the homework assignment. This is the final exam where the student is asked questions again, and then the teacher is not providing the answers. The student is supposed to write the answers, and at the end, you will match the student's answers and the teacher's answers to kind of know what the student did in this particular course. So this is exactly the same framework we use in machine learning. We split our entire data into a training data set and the testing data set. We use the training data set to build our model. We use it to our weight parameters. And then we use that particular trained model to do testing where we check its performance on unseen data set. So this is how a general machine learning pipeline would look like. You would have labels and you would have raw data. So this we discussed. Then you processing on top of it to prepare training data and test data. So this pre-processing, so like we discussed in our notebook, we removed the stop words, we converted the words into integers, we did the padding where we appended zeros in order to make vectors uniform, and things like that. So you do all sorts of pre-processing that you want to do on your data set, and then you split it into a training and the test data set. This is followed by a learning phase where you are using your learning algorithm. This is where you're using the gradient descent algorithm. So you have a W parameter, a slope of, let's say, a classification line that you're learning. So you're trying to learn a classification layer, which is nothing but a line with the slope W. And you are looking for that W, you initialize it randomly, and then you're using your gradients to update that W. That's the learning phase. Once you get this particular learned model, you evaluate it. So you get this final model, and this final model is then fed with the test data. Now, this is the same as the student being provided with the final exam. And then he or the student goes and gives the answers. These are the labels. And these answers are then checked by the teacher based on the test data set, the answers that teacher originally had, in order to find the accuracy or the performance of the student. So here, basically, this is called the accuracy performance of the final model. We keep doing these steps and satisfied with a particular performance of our data sets or of our model. So for instance, let's say requirement to pass in a course is 80%. So until unless this particular student receives 80% or more marks, this student would have to retake that class. And that's exactly what is happening here. Until and unless this final model achieves an accuracy of more than 80%, you keep on learning, you keep on updating the weights, you keep on updating, you keep on following the gradient descent algorithm to kind of keep making updates to your weight parameters, and then refine your accuracies. Once this procedure has ended, let's say the student has graduated, he has completed the course, he got a final grade, and now the student is out for a job. The student is out there in the job market, and now the student with test questions by the interviewer. Now the student would be answering those questions by the interviewed labels. And the interview would basically judge the performance of the based on what labels this student is providing. And that is called the inference phase or the prediction phase. That is, this is when the model is being deployed in the real life. So it is this till this phase of evaluation, till when the engineer has the control. An engineer has full control into the model to kind of update it, keep checking it, improve it, ask more questions, provide more feedback up till the evaluation phase. But once the engineer deploys that model, then the model is running in the world, it's running in the real world, it has to make predictions, and then it is being judged by the real customers. So I hope this machine learning pipeline is clear. If
One
there are any
second, madam.
questions.
I have one question. Can you show that machine learning pipeline, madam? Yeah. Here, after learning, we have to go for prediction, then evaluation, madam. Prediction, then only we can evaluate what is the testing, we can get the results.
So this prediction is the final stage of prediction, where the model is being, so like student is being interviewed by an interviewer. But here all prediction step is happening in this evaluation mode.
Okay.
Is predicting labels. This is a prediction.
Yeah. No, maybe you are telling after fine tuning, final prediction, this one. After tuning any parameters, that is the final prediction, what you are going to do in the last one.
Yes. This is actually inference rather than prediction. The prediction here, from final model to you predict, you get these predicted labels and you compare it in the test with the ground labels, and then you predict, you get the accuracies.
Okay.
This is once let's say an engineer has finalized his model and he has deployed it into the real
Understood.
world. So
this is after deployment you are telling.
Yes.
Okay, fine. Thank
you. And we have several other also for learning. There is unsupervised learning, where there's no label associated or label data available. It's very hard to get these labels. That's what is called unsupervised learning. And reinforcement learning is somewhere in between. You kind of know some labels, but you do not know all of them. So for today, I have been focusing on the supervised framework, where you have label training data, because we have a data set where the news articles have been labeled as fake versus real. and you can use the supervised learning framework to make the predictions. Okay, let's go back to our notebook here now. So like we discussed this machine learning pipeline, we will now split our data into train and test. So you can use this train test split library, which would randomly shuffle your input data. And then you can specify the size of the test set you want. So here 20% of my data as test set and the remaining data set as the training data set. So here you would actually get train and byte train, that is the raw data and the test and byte, which is again the raw data and the late. Now, this is where we are converting our words into numbers. Organize it, we fit it on the text. That is, we create the mapping. From each word, we assign it an index. And then this is in the vocabulary. So basically, this step would find all of the vocabulary in your data, and it would then assign a number to each word in your vocabulary, followed by for data. Now for each XI word that you have W1, W2, W3, then you identify the numbers corresponding to W1, W2, W3, and that's how you convert your to numerical form. Okay, so this is again has a lot of data here. While we can see here, I've pre-printed this one. So encoding for this document, budget, fight, looms, Republicans. So see, the word budget has been assigned this index of 384. The word 492. Republicans has been assigned 47, and so the entire document has been encoded to a sequence of numbers. And now we do this padding where we append zeros in order to make a uniform length vector across our data set. So here I've used maximum length of 40. So I'm creating a 40-dimensional vector. So capital D is 40 here. And I'm doing post as in I append zeros after the last word, and truncating means if the words, if there are more than 40 words, you just take first 40 words here. Now let's see for some of our documents how it look like. So if you can see here, this is a 40th vector. I have numbers associated for each of these indexes. So each word is represented by a number. And now each passage is represented as a 40-dimensional vector of numbers. Okay. So we did this concept of neural networks during the first session. And some of the participants also asked what are deep learning, what is deep learning and how is it different from neural networks? So neural networks essentially is one sort of deep learning network. There are other where you kind of use a lot of layers and a lot of neurons to construct deep architectures. There are some other specific neural network structures such as recurrent neural network. These neural networks essentially use time also. So instead of having a feed forward layer, so these are the feed forward neural networks that we discussed. You have the input, you have the hidden layer, and you have the output. In recurrent neural network, you also have an input going back from itself. So here, in this particular, the previous layer and its output to the next layer. But there's no input from itself. But in recurrent neural network, you have an input from itself. And that is like, what was the input at time t minus 1? So this time t minus 1 input can now basically affect the output at time t. So autoregressive equations, if anyone of you have heard of, is very similar to autoregressive relations where the output at time t is basically affected by the outputs at time t minus 1. So here again, this structure has been unfolded. So as you can see here, So this HT basically is being at time t, this being affected by the previous layer input, that is HT minus 1. That is at time step t minus 1, what was the output for the same neuron, and then the input at that time t, that is the new input at time t u. So if you see here, this loop has been unfolded into this time sequence where you have the output at time t being affected by output at time t minus 1. Why am I discussing about recurrent neural networks? You must be wondering. And the reason is that natural language processing is particularly suitable for recurrent neural networks because the words have meaning only when they appear in certain sequence. If I say John went to the store, you are able to understand what I'm saying. If I say words like John's store went to, then you'll be confused. Oh, what is she saying? So the words have meaning only when they appear in a certain sequence. And this particular aspect of language can be captured by recurrent neural networks because they have this time dependency. So what appeared previously should impact what can appear afterwards. So if you have John went to, then there is more likely the next word could be store rather than apple. So John went to Apple does not make sense, but John went to store, it does make sense. So the tendency of next word appearing given the previous words is essentially we want to capture in language understanding, and that is particularly useful for us to capture recurrent neural networks. Let me quickly remove this and then. Finally, we have come to this step of building and training the model. One last thing that we want to do is, we know that the number of tokens in our data set is very huge. The size of the vocabulary is huge. So we would like to kind of compress it into a lower dimensional vector. This technique is called principal autoencode. This technique is called dimensionality reduction. And it is one of the techniques for dimensionality reduction is principal component analysis. Another technique is autoencoder. If we'll have time in today's session, I'll go over PCA. But for now, just assume that it can basically compress a 10,000 dimensional vector to, let's say, a 200 dimensional vector. Okay, now let's use Keras library to kind of construct our model. This model sequential is just a constructor here. It is just saying, okay, I'm going to add a layer by layer this particular model. And then the first layer that I add is this embedding layer where I'm mapping the input word dimensional, that is vocabulary, to 128 dimensional vector. So here, this is, let's say, 4,000 something words in my vocabulary. I'm mapping all of that dimensionality to 128 dimensional vector only. Then I add this neural network. So by LSTMs are another type of recurrent neural network. We'll not go into the details here today. But essentially the recurrent neural network operating on the time concept that I explained just now. Once we pass this particular data through this recurrent neural network model, we'll finally pass it to a classification layer where you compress 128. So sorry, before classification, we are passing it through the non-activation function. So if you remember, for neural networks, it is essential to pass the network through a non-linear layer in order to avoid just using a big matrix multiplication only. That's like, if you want to use the power of neural networks, non-linear activations help you express non-linearities in your model. Otherwise, you're left with only a linear transformation. So we use a ReLU activation function, which is nothing but a simple activation function. Essentially, it would it will remove or convert all the negative values to 0, and it will keep all the positive values. So basically, the function is 0 comma x. Where this is the x ALU output. So this is max of 0 comma x. You remove all the negative values. So if your input had negative values, they get converted to 0. But if you had a positive value, that's kept as it is. Okay. So now so we have added this nonlinear activation followed by sigmoid layer because we have classification for 2 classes. So this is like the 2-dimensional version of softmax. So this, you're using just 2-dimensional version of softmax layer that we discussed earlier. And then you compile it. The loss function that you're using is the cross entropy loss function that again we discussed earlier. And then I'm using accuracy to measure the performance of the model. So model predictions, and I'm going to test it against the labels that I have and calculate the accuracy. And model.summary would essentially what does look like and how the model looks like and the trainable parameters, etc. So here, if you see, have an embedding layer that will map high dimensional vocabulary to 128 dimensional vector. Then you have recurrent neural network that will do some processing on the input text to capture dependencies among words. And then you have a dense layer, which will map 256 to 128. And then finally a classification layer, which will tell you news article real or is it fake. This is the sigmoid layer where you're using dimensional version of softmax and you're predicting whether a particular article or not. So if you see here in this just neural network, you have a huge number to enable parameter the variables in your theta vector. So if you remember, all W's, B's, biases that we have, etc., all of them are trainable parameters here. Okay, now let's just get the training data. These are the labels. And now we're going to call .fit, the training data set, the training labels, with the batch size, validation, and epochs. Epochs is the number of iterations that I'm going to train this model for. So for 2 times, the gradient descent algorithm will be run on entire data set. So now you train the model. And it's going to take some time because now this particular step is actually performing the gradient computations, back propagation computation, and then updating weight to do the training. And here, as you can see, iteratively accuracies are improving. So we are already at 92% accuracy. So let's see how model is performing. Is anyone having any questions? So there are some mini challenges that you can try out later on. You can change the embedding output dimension, and you can see model parameter changing. So you can basically change these LSTM layer inputs, output dimensionality. Maybe you can try 240 or even higher to just see how the accuracy changes, how the trainable parameters changes, etc. Okay, here you see, here we have, this is the training accuracy, the 98.57. And then we had this validation accuracy, that's the 99.75. So if you see, we had this step, this evaluation step is what we are learning, and evaluation is the two steps we are running together right now. Learning will give you some accuracy, that is the training accuracy. And in the evaluation mode, I'm calculating the validation accuracy, a small homework assignment where the model is evaluated for its performance. Okay. So now we can see that our model has achieved great accuracy, as in training accuracy is 99.96 and the validation accuracy is 99.78, which is huge. Like this, it seems students is very intelligent. Okay, we'll go and on the test. This is also a part of the evaluation mode that I showed in the pipeline. We're still here in, now I'm testing. This is the final exam for the particular student. So you do a model.predict in order to predict on all of the data samples in the test set. Okay. And now if you look at this is just going to be a single value for each sample. So if you see the shape of this prediction, it's like 8,980 samples were there in our test set, and it predicts one value for each of these samples. So let's see some of these values. See here, okay, this is a number one. Now let's see another value. Again, this is a number which is very close to 0, but again, it's a positive number and it's between 0 and 1. These numbers can be treated as probabilities. So Asim use this fact to make final classification. So if the item has more than 0.5 probability, we'll call it 1. If otherwise, we'll call it 0. So let's make this hard class prediction. So now let's look at what our predictions are. This is just like a thresholding where I've used the threshold of 0.5, make the decision whether I call it 1 or I call it 0. And if you see the prediction values for, let's say, top 10 values, you will see there's a zeros and ones now. Now let's use these predictions to get the final score for this particular model, that is the model accuracy. Let's run this and we see that the model has a very high accuracy of 99.52%. Another way to kind of see the model performance is to see true positives and false positives and true negatives and false negatives. This is basically a confusion matrix. Essentially, what you're trying to do here is you have a positive, let's say label, negative label, and then again you have a positive and negative label. You count how many, and this, let's say this is true and this is predicted. This is predicted by the model. Sorry for my bad handwriting here, but okay. So this is basically of number of samples where it was positive and the prediction was positive. So these are called true positives. TP. It's abbreviated. This number tells me how many were truly positive, were wrongly predicted as negative. So these are false negatives. So they are wrongly predicted as negatives. Again, here, this one is how many of them were truly negative, but predicted positive. So these are false positives. They're wrongly predicted by the model as false positive. And then again here, this is true negative. How many were actually negative, were predicted negative. So this is true negative. This particular confusion matrix, general, more useful balanced data set, where the number of classes you have in your positive class and the negative class quite different. So let's say you have 100 samples of positive class, but only or 3. In that case, it is very important for you to know how is this distribution rather than just mere accuracy, because even if the model predicts all of those 102 samples, if you're just making 2 mistakes, and the model is going to have a great accuracy, but essentially it's not learning anything. For our case, note that this accuracy is also a good measure. Reason being, we had a balanced data set. The number of samples for fake articles and the real articles was actually very balanced, very similar. We have roughly, so I guess one of the participants also said, and we plotted it. So they had roughly equivalent numbers with fake label and real label. So now let's go back. Okay, so here we see this is a confusion matrix that I've plotted here. And what this essentially is saying is the lighter the color is, the higher the value is. So this is saying 4.7 e⁻03, that is 0.7 into 10 to the power 4.7 thousand basic samples. Essentially, this is saying that the accuracy is good because there we have a lot of true positives and true negatives, but very less of false positives and false negatives. And that is the goal. We don't want false negatives and false positives. We only want true positives and true negatives to be very high. Okay, so now we have done this, and congratulations, we have like built a very great fake news detection classifier that we can now use to make predictions. And let me remind you, for 0, we are using fake news, we call it fake, and for 1, we call it real. So, okay, we graduated the student and let the student go to an interviewer now where the model is deployed in the real life. And I have kept a few test examples. So I tested these examples, and feel free to kind of share any news articles that you would now want to test on this particular data set for this particular to see. So you may know whether this are true or fake, but I don't know, and the model has to make the predictions. So for instance, I kept this example from one of the Indian news today, the inauguration of Sri Kashi Vishwanath Dham corridor by Prime Minister. And this is a genuine is public. What is our model predicting for this particular news? So we do all the pre-processing we needed. We did on our training data to keep everything similar. And let's see. Okay. The model is saying fake. So the model thinks that the inauguration of Sri Kashi Vishwanath Dham corridor by Prime Minister Narendra Modi is a fake news. Okay, maybe this is one small mistake that this particular model is doing. Let's try another news. Let's try one from US now. At least 90 people were killed by the devastating storms on Friday night, including 80 in Kentucky. Again, this is a genuine that I have picked up from one of the reputed sources. And let's see how is that performing. Okay. So again, this is also saying fake, but with very low probability. Now, next, let's look another example where voted 5 on Sunday, taking the tally of the cases new variant to in the country to 30. This is, of course, a very genuine and a grave news. This particular model should be able to predict that this is a real news. Again, fake. Okay. Something is going wrong with the model, as we can see. Let's try another last example here. Now, South African President Cyril Ramaphosa tested positive for COVID-19 on Sunday and is receiving treatment for mild symptoms. This is again a genuine news that I have picked up. And the model is again predicting it as fake. Any of you like to kind of test this? Feel free to post any URL. We can use it to kind of check a news article, or let me pull up a news article today. Any of the favorite news articles, if anyone has. Okay, a lot of pop-ups. Okay, so this news is about army kills 14 civilians in Nagaland. So let's use this. I've randomly picked an article in front of you. And I'm going to give this text as an input to the data, to the model. Let's see. Again, fake. Any ideas, anyone, why this is happening? Why our model has so accurate, so on paper? But when we are into model, it's performing stable. It's calling all of the genuine artists fake. Anyone? Feel free to say anything. There are no right or wrong answers here. This is an open research problem. So I would be actually happy to kind of see fresh ideas here. Like, what do you think was wrong? We followed everything that's the machine learning textbook says. We did the pre-processing, we did the training, we did the evaluation, we did the validation, we did the splits for training and testing. So what went wrong? So Mayanka has a very good point. This is trained on US news, and Indian news may not work well. That's indeed a very brilliant observation. Any others? Come on, I want to listen the ideas today here. Uh, why is this happening? This seems to be very, can you even deploy a machine learning model for such system critical applications? Right now I'm giving an example of fake news, but let's say tomorrow I want to say whether a patient is tested positive or is it tested negative for COVID-19. Can I rely on such a machine learning trained model to make predictions in the real life? That could be life threatening if for every patient, the model is saying not negative, even if the person is. Or maybe if it is saying positive, even when the person is not positive. This could be life threatening for. Okay. One of the reasons why this particular model is not performing on the news that we checked out today is the data distribution. This classifier is trained on news articles from 2015 to 2018. And if you see in 2020, we saw a drastic change in the reportings of news. COVID-19 becomes way more prevalent in the media or the mainstream media, and the vocabulary completely changed. So if you see here, the data distribution has been changed completely. Words such as COVID-19 or maybe vaccines. So vaccine, for instance, was being used earlier, but was not so frequently cited in the news articles. But after COVID happened, the word vaccine was appearing over and over again in the news articles. And that's a shift in the data distribution. So let's consider this toy example where the data is denoted in the blue dots here. And this green line is the learned function. This is the model that we have as of now, which is trained on 2015 to 2018 news articles. But the true function, which we don't know, that's the real function that is hidden from us, is the red curve. which looked very similar to the green curve for the data we had, because we had access to these blue dots. But when we tested this particular model in the real life scenario, we encountered these black star signs or the crosses, which are significantly differently distributed as compared to the blue dots. That's the training data. So there's a shift between the training data set and the test data set distribution. And this happens because there was an event that happened which was not very much anticipated, and it caused a huge shift, a huge paradigm shift in the kind of words we were talking about, kind of words we were, kind of topics we were talking about, kind of we were having in our day-to-day lives during the pandemic. So that was the data distribution shift, and that's one of the reasons why this particular model is not able to predict correctly on COVID-related news. Another reason is the demographic biases. Like Mayanka said, the classifier is trained on news articles which are reporting events in United States of America. And therefore, this classifier is performing terribly on Indian news. Words such as Modi or the name of the religious places or name of the our government officials, etc., are not so common in United States of America's news events as compared to Indian events. Again, become out of vocabulary words or new words for the model, which the model cannot recognize. Those words are essentially not there in the model's vocabulary. And therefore, it loses the essential to make these predictions. So classifier can perform terrible because of the vocabulary and also the style of reporting. The way the English is being reported, the English language being used in United States of America is slightly different from the English we use in our Indian news articles. The style of reporting could be quite different, even across Indian states. So if you have a newspaper article written in Hindi language, let's say in northern part of India, versus another article written in Telugu language in southern part of India, those style of reporting can also be sometimes very different, even when translated to a common, because we have our own demographic biases. We want to portray some of the entities in a more favorable light as compared to others. There could be genuine changes in the language use, there could be changes in the dialects, etc. So there is a question by Gurvinder who's asking how to confirm that the model is well trained. So one metric to model performance, you see validation accuracy, testing accuracies. And we saw that those accuracies were great. But when we tested it in the real life, the model did not perform very well. There is this research area of adversarial testing, where you kind of do not release the model until your model is performing well on adversarial data sets. So the examples that I used from India news articles are actually adversarial, because I know that this model has been trained on US news. It's very hard for it to predict on Indian news, and those are adversaries. So essentially, the idea is to construct a test set which is representative enough of majority of the use cases where this particular model will be used. So for instance, in our situation, having news articles from across the globe would be a viable option. Even if you cannot have a huge amount of data labeled from across the globe, having a reasonable representation, a reasonable balance between articles from US, UK, India, and abroad, and any other country would be a good way to kind of ensure that the testing accuracies that you're getting are the real measure of the model performance, and is not just a mere artifact that you're observing because your test data set is itself too easy for the model. And sometimes there are other, so I guess there's a hand raise. Yeah, please go ahead.
Ma'am, I have one basic question here. You're talking about the training data, right?
Mhm.
So, hello.
Yeah, go ahead.
Yeah.
You're audible, Doctor.
I'm audible, ma'am. Hello.
Go ahead.
Hello.
Yeah,
Okay. Ma'am, while performing the data, there are some few mistakes which we generally do. So you have already pointed out the few mistakes like the the solution bias or sampling bias, might be the overlifting. So can you just tell me how to avoid these silly mistakes while doing the training data?
while doing the training data.
Yeah.
So sampling biases and essentially when you're doing sampling biases can be avoided by doing random shuffling most often. You can also try doing bootstrap sampling. For instance, that's a process where you pick a random subset of your actual training data and then train the model. Then you pick another random subset of your training data and you train another model. And you can keep on doing this to kind of create an ensemble of your models. So instead of having one expert classifier, you have many other classifiers who can make predictions for you, and they are based on different subsections of your training data. So they would each be capturing different biases, but when you take a majority vote across all of them, those biases can be eliminated. So that's one way of handling these sampling biases when you're doing training data preparation. Of course, random shuffling is very important. Sometimes the model can merely learn the relation between the index. That is, if the sample
Yes.
is appearing on the data, then it's fake, and if it's appearing low on the data set, then it's real, for instance.
Ma'am,
And
for
it's
example,
important to make
my question was that, for example, the training data is communicating poorly.
Mhm.
Okay, so how can we like neglect that part? So can you show that with an example if possible?
What do you mean
Like
by training data?
while performing, like while training the data set only, it will communicate poorly sometimes, right? So how can we avoid that mistakes, or how to like identify that mistake and how to overcome that at the training time only?
uh, I'm not able to understand by communicating wrong signals. Are you saying that your training data has noisy labels, as in
Yes, sometimes it will easy to slide into a few traps, right?
okay, so there is this the problem, as I understand, is the problem of noisy labels in your training data set itself. Like
Yes,
sometimes
yes,
the label is true, but actually it could be fake as well. So
correct.
you are like only 80% sure that you're true
Yes,
fake.
yes, yes.
There are methods for that. One method is to kind of do active learning.
Mm-hmm.
Here, what you do is, let's say you know which samples the labels for these samples are very clean. You assign a high weight to those samples. So let me. Okay, let's say this data set, right? And you know labels for each one of them. Suppose that's the label. And you know these two samples, you're very sure, because let's say some expert has given you this label. But then these two labels, you're not very sure. What you can do is you can assign weight to these labels. So you can assign a very high weight to these, let's say 0.8, you have 0.8 confidence that these labels are very good. And you can assign a very confidence to these labels. You think these are noisy. And now you can use these weights in the cross entropy loss. So let's go back to the slides. So here, if you see, here for each sample, you have this loss. And you want to penalize the model only for where you are very confident. So let's say the loss is high on these two samples where you have 0.8 confidence that these samples are really very good, then your loss should be very high. So if you're making a mistake here, if you call this 0 as 1, then the loss will be very high. But let's say you're making a mistake on these noisy samples where you're yourself not sure if this is a good data point. There you can reduce the penalty that is done to the model. Like you can reduce loss function. So you're not taking the contribution of a mistake on this particular sample as much as you are taking the contribution from these samples. So this is called, this training framework is quite popular for training with noisy data. Another way is you can then followed by this training mechanism, you can then make predictions, and then you make predictions here on the samples which you are not so confident. And you can also then ask an expert human annotator of only sample of your data. Wherever your model is making very good predictions, you don't show that to the human annotator. But wherever the model is making very bad predictions, you show those to your human annotator to get additional feedback. So that's the active learning framework where you use humans in the loop to make better predictions.
Okay, thank you. Thanks.
Okay, so I'm almost there. I have quickly few more points to make. Let's get back to. Okay, so we were talking about these demographic biases, and all I want to say is that these demographic biases are quite prevalent in all of AI, not just fake news detection, not just COVID detection, but everywhere. So for instance, there was this study where African American and Asian faces, they experience 100 higher false positive rates compared to faces, that is the white faces, when it comes to facial recognition algorithms. So many of you might be using iPhones where you use these facial recognition algorithms to kind of to unlock your phones. And it has been observed that algorithms make a lot of mistakes on African face as compared to primarily West faces. An issue because this is these algorithms that we are building, the methods that we are building, they should be suitable for everybody. Should not be making discrimination based on your demographics. And this is again how this discrimination is there right now in the research area of machine learning and AI in general. You have some biases are created because you have unequal accesses and resource allocations. So for instance, companies such as Google, Amazon, etc., they have huge accesses to GPUs and other data storage devices, etc. They have huge data where they have huge compute power, and they are particularly strategically very strong in use machine learning and deep learning frameworks more quickly with better other biases because of discrimination, that is sampling biases like we were talking about. Right now, this data set that I had access to was actually built upon US news articles, but the question naturally arises, why not other countries? Why were the articles related to UK or other Asian countries was not included in the data set? There could be biased decision choices because of these deployment practices. So say power imbalance can happen. Sometimes these AI algorithms are used for maybe resource allocation. So for instance, HR, sometimes there is work going on predicting whether this resume should be taken forward for the interview on AI algorithms. And if you are making mistakes, on, let's say, more females than as compared to males, then that's an opportunity cost. You are kind of taking away opportunities from certain sections of society, and that's very terrible. That needs to be handled in such critical applications. And yeah, so application injustices again, for instance, there is research going on predicting whether a particular criminal should be provided bail or not. And it has been found more often that African American criminals with African American demographics are less likely to be predicted that they should be given bail as compared to white Americans, because just because a person is African American and not primarily the bias encoded in the algorithm, that person is being subjected to these punishments, which may not be fair. So that's why there's a lot of debate going on right now, and the researchers are very cautious of using these AI or ML algorithms for such system critical applications, criminal, any other opportunity allocation processes such as resume filtering, etc. The consensus right now is that we are far away from such applications. We need to be very careful in making such choices. And lastly, there is another issue with this fake action model that we had today. None of us questioned. So let's say if tomorrow Facebook tells you if this particular article is fake or not, would you believe it? Without even any explanation, would you believe if Facebook says, oh, this article is fake? Don't. Probably not. Even in multiple choice questions that we give to our students, we ask them answer yes or no and explain why. Why do you think the answer is yes, or why do you think the answer is no? So explanations are actually a very important integral part of human understanding, and such machine learning algorithms cannot be expected to make decisions or recommendations without why they are making those decisions. So currently it is going on in explainable AI, where you not only make predictions, but also make explanations. You predict, you tell why you are making certain particular predictions. So for instance, if you are making a human, if you are having an algorithm which says a person is sick versus she is not sick, you can probably symptoms making those predictions. So if the model is a headache as a symptom for a particular person, this is not. But if the appetite and a fever, then that's a of being. Such explanations such as led you to predict which words led the model to predict whether a particular news article is fake or not can be very helpful. Then these explanations can then be provided alongside the decisions made by these ML algorithms, so that we humans, we as consumers, can decide for ourselves whether we want to believe this particular prediction or not. So let's say if an HR is basically reviewing resumes and certain resumes are rejected, the model should tell what were the reasons based on which the model predicted rejections. And if those rejections are maybe because of any demographic biases, then the HR recruiter can basically say, okay, I do not want to trust these model predictions, and I want to go over these resumes by myself. And lastly, there is problem with problem formulation of a fake news detection. We started with this problem formulation where we said we'll give an input article, we'll train a classifier, and we'll just predict fake or not fake. But I suggest that this problem formulation has major flaws. One of the flaws is that entire news article is often not fake. Sometimes some claims are there in that particular article which are fake or false, but the rest of the news articles looks pretty fine. What do you do in such situations? Sometimes all the facts are right, but all of those facts are right. But then in the end, the the author of the news article is saying, oh, because Pfizer vaccine has this much accuracy, and then this particular biotech vaccine has this much accuracy, so let's not use these vaccines because they're all bad for our health. Numerical accuracies of different vaccines are right, but then the conclusions are wrong. And now, do you call that news article as fake or not is questionable. And sometimes things are often presented out of context. So you can have everything written right, but then a picture of somebody else being transformed and cited with some other context can make them look very wrong. The things being presented out of context is also a very common form of spreading fake news. And those are the certain aspects that we did not take care of in today's formulation. So even though on paper we achieved a very great accuracy for 99% accuracy for fake news detection classification, the process information is far from being solved. We are just on the right onset of even trying to solve this problem. A simple classification model is probably not the right formulation for this complex problem. So there are several ways forward to kind of solve this problem. You should also look at image processing. Whatever images are being provided, are those images doctored? If those images are doctored, then there's a high chance that this news article can be fake. Who is the original source who's reporting this particular article? Is this a very reputed media house, or is it a media house you have never heard of? How often this particular article is being shared over Twitter or Facebook or other social media. If it's being spread virally, then it's probably fake news, because if that particular article is being spread, is having millions and millions of tweets and links, probably there's something worth noting about that particular article. And we of course did this textual analysis of text analysis using machine learning and contextual reasoning today. But again, like I discussed, there are some important aspects of this text analysis that we need to think about in more detail. And finally, automating the process of fake news detection end to end is somewhat very ambitious as of now. A more reasonable approach would be to have a journalist or somebody who is an expert in this area to kind of look at a news article which is being predicted as fake by a machine learning algorithm, and then humans make the final judgments of whether this particular article has to be retracted or it has to be reported that it is fake or is it not. So human in the loop is essentially a big framework that could be helpful in tackling misinformation. So that's all. I would urge everybody here is to be responsible while using artificial intelligence. It has a huge potential, but then if not used carefully, it can lead you to many pitfalls. There's ethics and regulations and governments. It can cause opportunity cost for millions and millions. We as engineers are primarily responsible for making the right decisions while building such machine learning models and using them and deploying them in the real scenario. Thank you, and I would be happy to answer any questions.
Any questions from the audience? Okay, so thank you very much, Ankita, for your exhaustive, informative, and very excellent presentation. And I feel the topic also was very apt in today's scenario. So most of us go through these kind of issues, and when there are so many WhatsApp forwards coming to our WhatsApp groups, so we will not know which one to believe, which one not to believe. So I think you have really given a very enlightening session on that. Of course, it requires a lot of research and knowledge about this neural networks. So I'm sure people who are already working on this area would have got many good inputs on how to work on neural networks. And people who are looking for an exciting research problem to carry out their research, maybe in their initial stages, they also have got a good idea and they can think of pursuing their research in this area. And for rest of the people who are interested in this, or if they have any other questions, I think they can always reach out to us or to Ankita directly for any of their queries or any of their doubts what they have. So thank you very much, Ankita. I think I will request Dr. Chitra to conclude the session if there are no questions from audience.
Thank you, Ankita. That was a really session where, there were many insights and people had a great experience in learning many things. And in terms of, I hope I'm audible.
Yes, yes.
Okay. So any questions from the audience? You're most welcome to put out your questions.
From my side?
From the audience, any questions?
I think Mayank has written something. Can just read that.
Let me just read out to you. Okay, thanks for the insightful talk. Ma'am, can you talk about the current research and the research topics in the industry for AI and ML?
Yeah, I would love to answer that question. As regards my current research, I am actually actively involved in identifying racially targeted misinformation. So we are identifying really targeted misinformation on different sections of the world. More often, even Asians are targeted in different parts of the country, more targeted in terms of misinformation as compared to other demographics. And even more speech is being targeted at certain sections of the society. So I'm currently working in that area, and broad area of my research is natural language processing and understanding, where I try to see how machines can understand the languages we use. In different languages, I barely speak Hindi and English, so I'm working in these two languages as of now. But how we make machines more robust in understanding these languages? How can you build models which can predict things such as language generation? Can the machines be used to generate text? Can they be used to generate stories automatically? Things like that. So that's one area of my research. So yeah, regarding the research topics in industry for AI and ML, I would say machine learning and AI is the hot topic as of now for industry, and a lot of industries, not just the software industry, but even the core industries such as maybe Reliance and others, which are not primarily technically software oriented, but have been in the core business for long, are also kind of moving towards AI and ML, and the potential of AI and ML is endless. So for instance, GE Healthcare is currently using AI and ML for their applications. I'm more familiar with software industry given my own background. So for instance, Samsung works on face recognition, video enhancing using these AI ML algorithms. They voice assistants, which is called Bixby, to kind of use natural language processing to answer the questions. It is very similar to Amazon's Alexa or Google's assistant, Hello Google. I in particular again worked on misinformation at Samsung. Amazon again has a huge business model where they are using machines to predict which deals they should offer you. So based on your purchase history, and if you would like to permit, they would like to recommend you certain products. They would recommend you ads that you might be interested in. They recommend you the deals that you're interested in. So that's another area of research or where industry is at the forefront as of now. I hope that answers. In general, NLP, speech processing, image processing are the key areas where software industries are oriented. Medical healthcare is another area which is coming up as of now. But like I said, the medical healthcare area is way more cautious because it is a system critical application where lives are at risk. So the researchers have to be extra careful.
That was very informative, Ankita. Thank you so much. I request all the participants to join post-lunch, and the feedback link is also posted on the chat box. So you can provide your valuable feedback. And thank you so much. Bye-bye.
Thanks, Ankita. Thanks a lot. Yeah.
Thank you.